Okay, so the last section of Unit 3 is called molecular formulas. So this is going to be very similar to what we did in Section 3, okay, with empirical formulas. However, there is one additional step at the end that we will need to take care of. Okay, so empirical formulas, just a reminder, we talked about this just before, they do not always indicate what the actual compound is. Okay, so they might give you the simplest whole number ratio, but it may not be what the actual compound is. A molecular formula, okay, it's a chemical formula which specifies the actual number of atoms of each element. Okay, the actual number of atoms of each element in one molecule or formula unit of the substance. So, for instance, we talked about this in the last section. We could have an empirical formula HO, 1 hydrogen to 1 oxygen. Okay, but the actual formula might be H2O2, hydrogen peroxide, for instance. Okay, the molecular formula is the correct formula, what it actually truly is, and it's H2O2. Okay, versus an empirical formula, which is just the simplified version of this. That's the difference between that. An empirical formula doesn't always indicate what the actual compound is. It indicates what the smallest whole number ratio is. The molecular formula indicates what the actual formula is. So we'll figure out how to do that. Okay, so the problem is to determine the molecular formula of butane, given that its molar mass is 58.14 grams per mole and is 82.6% carbon and 17.4% hydrogen by mass. Okay, so the solution to this, it's going to be just like solving for butane, the empirical formula of butane. We're going to assume 100 grams of it, just like we did before. Convert the grams into moles, find the smallest whole number ratios, use the molar mass of the compound to find the molecular formula. Okay, so here we go. Determine the molecular formula of butane, all right? It's just the problem right up there. Okay, so if it's 82.6% carbon, we assume 100 grams of it, that's 82.6 grams, that is carbon. Divide by the molar mass of carbon of 12.01 grams per mole, that's from your periodic tables. You get 6.88 moles of carbon. Okay, molar mass of hydrogen, the mass of hydrogen is 17.4 grams. Hydrogen divided by its molar mass, which is 1.01 grams per mole, that gives you 17.23 moles of hydrogen. I gave myself an extra significant figure there, so that my answer in a moment is going to make more sense. Okay, and then we divide just like we did previously on the last homework. Divide by the smallest amount present. Well, the smallest amount present here is 6.88. So divide both by 6.88. You get 1 mole of carbon for every 2.5 moles of hydrogen. Okay, so that's a very interesting way of looking at this, because right now, normally we could just write its formula as CH2.5, but that doesn't make sense. We can't leave an answer like that. We've got to get it in a whole number ratio. Okay, so what we're going to have to do in this instance is multiply it to get it into a way such that it is with a whole number ratio. Well, this is 2.5. To get myself to a whole number, I could multiply anything that ends in 0.5 times 2. Okay, so the smallest whole number ratio here is C2H5. That is my smallest whole number ratio because I can't leave this as 2.5. You might have experienced some of that on the Section 3 homework. Okay, you might have encountered one that ended and you thought, well, that's weird. I can't have a third, like 0.3333 repeating, or 0.25, or whatever, 0.5. You can't end with something like that. It's got to be a whole number. Okay, so we can't have that. We said it's got to be whole numbers. Therefore, we multiply all the ratios by 2, and we end up with the empirical formula. We just said this, C2H5. We can't have this. Don't leave it as CH2.5. That's not a thing. It's got to be a whole number ratio. Okay, so now, how do we figure out what the actual formula is? Is it C2H5? Well, we know what the molar mass of the whole compound is given for butane. It's 58.14. We need to figure out, is this the actual formula? Well, how are we going to do that? We are going to first calculate the molar mass of it, of C2H5. Well, 12.01 is 1 carbon times 2, that's coming from there. And 1.01 is hydrogen times 5. That gives us 29.07 grams per mole. Okay, so this is for 1 unit of C2H5, 29.07 grams per mole. Okay, so now you're supposed to compare the molar mass of the empirical formula with the molar mass given in the problem, the molecular formula. So I took the molar mass of the molecular, this one right here, divided by the molar mass of the empirical, 58.14 divided by 29.07, and I got a very nice, pretty 2.00 ratio. It's a very nice, easy to work with ratio. So what does that mean? That means that my molecular formula is twice that of my empirical based on the molar masses. Okay, therefore the molecular formula is 2 times that of the empirical. So C2H5 is not my formula. My molecular formula for butane is C4H10. That is the correct formula for butane, C4H10. And we know that because the molar mass given up here in the problem was 58.14, not that 29.07. If it had said up here at the beginning, yeah, the molar mass is 29.07, and you got 1, well, that means you're done. The molecular formula can be the empirical formula. Okay, it can be that. Back when we were talking about empirical, we said it could be the actual formula, but it might not be as well. Okay, so it just depends on what you get up here and what the molar mass of your empirical formula is by itself. Okay. So let's try another one here. Stearic acid is a saturated fatty acid containing carbon, hydrogen, and oxygen. So this is back from biology. Maybe you learned about it. It's common in things like meat, steak, turkey, chicken, things like that, stearic acid. Its molar mass is, okay, it's a big one, 284.54 grams per mole. It's composed of 76.0% carbon, 12.8% hydrogen, and 11.2% oxygen by mass. What is the molecular formula of stearic acid? Okay, so what is its actual formula? It's going to be fairly large based on what we know up here, but it could be any combination of carbon, hydrogen, and oxygen. So solution, begin by finding the empirical formula of it, right? We assume 100 grams, convert the grams to moles, find the smallest mole ratio, divide by that. Okay, then we're going to use the molar mass of the compound to find the molecular formula. Okay, so we got 3 things. We got grams of carbon, 76 grams of carbon divided by its molar mass. We get 6.33 moles of carbon, 12.08 grams of hydrogen, divided by 1.01 grams per mole. We get 12.7 moles of hydrogen. And down at the bottom here, converting the oxygen over to the number of moles, 11.2 grams of oxygen divided by 16.0 grams per mole. We get 0.700 moles of oxygen. Okay, so our next step is going to be divide by whichever one is the least, and that is that number right there. So divide them all by 0.700. We get 9.04, 18.1, and 1.00 moles of oxygen. Okay, so again, you got to remember these are measurements. They're not exact values. So we're looking very, very closely to 9, 18, and 1. Okay, 9, 18, and 1. So the empirical formula we've come up with, again, C9H18O, right, O1. Well, we find the molar mass of that, okay, molar mass of that whole thing, that turns out to be 142.27 grams per mole. All right, so it's significantly less than this. What's the ratio? What's my number? Well, then I need to compare this number to this number. All right, and if you're looking at it, you can kind of see a relationship already. Okay, so we're going to take the molar mass of the molecular divided by the molar mass of the empirical. We get a nice, even, once again, 2.00. Therefore, the molecular formula is twice that of the empirical formula. Stearic acid's formula, then, is double what it was empirically. So it ends up being C18H36O2. So it's a pretty lengthy compound there, 18 carbons. Okay. But that is its formula. Its empirical formula was C9H18O. Okay, it ended up being double that based on our numbers. So let's try a problem in your homework together. Number 1. Okay, the first one here says vitamin C. Okay, I got to determine the molecular formula of this. I got to find the empirical and molecular. All right, so vitamin C. So this is number 1. It is 40.91% carbon. It is 4.59% hydrogen and 54.50% oxygen. Okay. So let's go ahead and convert these all over to number of moles. 40.91 grams of carbon divided by 12.01 grams per mole. All right, that's going to be 40.91 divided by 12.01. Okay, this is with three significant figures, 3.406 moles of carbon. Okay, for hydrogen, I got 4.59 grams of hydrogen divided by 1.01 grams per mole. So 4.59 divided by 1.01. That is with three significant figures, 4.54 moles of hydrogen. Okay, and oxygen. Last one, we got 54.50 grams of oxygen divided by 16.00 grams per mole. Remember, all the molar masses are on the periodic table. And that is going to equal, let's see, 54.50 divided by 16. We got 3.406 moles of oxygen. Okay, so our least in this situation is 3.406. So I'm going to divide all of them by that number. Okay, so this kind of works out easily because that gives us 1 mole of carbon. Okay, so 4.54 divided by 3.406. Okay, we get 1.33 moles of hydrogen, and we got 1 mole of oxygen. Okay, so now we got this kind of weird situation. These two are each 1. This one is 0.33. Well, this should send a red flag off to you because 0.33 is kind of looks like the fraction 1 over 3. Of course, that would be repeating. But that should kind of set off a red flag to you like, okay, well, this is 1/3 of something. So what I need to do is multiply this times 3 so that I can get rid of this decimal and end up with whole numbers overall. So all three of these are going to get multiplied times 3, okay? And you'll see how that works here momentarily. So then we're going to end up with C3. If you take 1.33 times 3, you're going to get H4, let's see here, 1.33 times 3. Yep, 3.99, okay, which is for all intents and purposes equal to 4. So H4 and O3. Okay, this is my empirical formula. All right, down at the bottom, you can go ahead and fill that in. C3H4O3. Some of these other ones are going to be quite big. Lipitor is a large molecule. Some of these other ones are quite big, okay? This one's got a fairly small empirical formula. We need to figure out what its molecular formula is. We need its molar mass. So let's find the molar mass of this thing. We got 3 times 12.01 grams per mole for carbon, plus 4 times 1.01 grams per mole for hydrogen, plus 3 times the 16.00 grams per mole for the oxygen. So the molar mass of this whole compound, all right, it is going to be, let's see, 12.01 times 3 plus 4.04 plus 48. This is 88.07 grams per mole. That's the empirical formula's molar mass. Okay. All right, well, I'm going to move this on to the next slide because I'm not out of room here. So I've got 88.07 grams per mole. That is for the empirical formula. Now I need to take the molar mass of the molecular formula and divide by that. Well, that's on the problem. It's 176.14. It's the third thing down in the problem. So if you're looking where that's coming from, that's where it's coming from. Divided by 88.07 grams per mole. If you can picture ahead here, you can see right where this is going. Okay, that's a nice even 2.000 ratio, which means my molecular formula is 2 times that of the empirical. Well, my empirical formula was C3H4O3. That was the empirical formula. Well, if I double that, that's going to be my molecular C6H8O6. And that is your answer down there at the bottom. That's what we are looking for. Okay, so like I said, some of these are fairly lengthy. Lipitor is a big molecule. Zocor, estradiol, those are all used in the pharmaceutical industry. Okay, so those are quite large things. You might end up with some interesting results. If you need to, check your answers on the internet. You can look them up there, but I advise you not to do that until you've given it your best shot. Okay, so go ahead and finish up Unit 3's work there on page 7 and 8. Give it a go for 2, 3, and 4.